thanks to these and many other people. You can ask me later for what. Oh, let's see. Right. Suggesting that, OK. Oh, I think these are familiar problems, right? Non-convex is always an issue. OK. Do I have the wrong talk? No. I want to give you some hope. So this is the reason. Is the brain or your brain a computer? So here are a couple of opinions. Face it, your brain is a computer. I don't know why he says face it, but something. I mean, so what if you? Anyway, and then your brain. No, even more dire. Your brain is an algorithm. Forget it. Okay, that's it. You just have to figure it out. Okay. Yeah. So, well, but more concretely, I guess it's it's reasonable to ask, how could the brain possibly accomplish all that it does? I mean, why am I talking about this? It is evidence of non-convex something, right? All of this is this is an A, and get your computer to recognize it's an A. I mean, I will be thrilled. But okay, but other stuff, you learn to swim. Okay, can you describe to me exactly how to swim so I can follow the directions on okay. Language, right? After a few finite sentences, most of us speak mostly correct sentences, which you've never heard before. Find a plausible explanation for this, just some way to do it, okay? So there is evidence of something not convex. To ask this crisply, how does the mind, invariance, language, learning, emerge from the brain, neurons, synapses, plasticity? Now I could replace mind here with all the crazy stuff that neural networks do, and brain with your favorite architecture that's running right now. This is from the most recent Nobel Prize winner in neuroscience. We don't have a logic for the transformation of neural activity into thought or action. I view discerning this logic as the most important direction of neuroscience. Again, here you can replace neuroscience with AI, and maybe most important with something else. Yeah. Okay. So here is a sort of a modest proposal, or really an extension of an idea that's already around in neuroscience, called neural assemblies. And the idea is alarmingly simple. An assembly is a subset of neurons. Okay, so you've got a whole bunch of neurons, an assembly is just a subset of them. And more generally, it could be, instead of being just a 0-1 set, it could be a distribution. And the point is that each assembly represents some idea. It could also be a meta idea, but it's a concept. Now, so for example, if you're thinking of panda, there's some subset of neurons that fire for panda, and simultaneous activation of most of these corresponds to this concept being recalled internally or because of stimulus or whatever. That's an assembly. Okay, here's a hypothesis that assemblies are the primitives of computation. That basically using this notion of assemblies and the very little mechanisms that the brain might be doing spontaneously, can you explain all of the higher level behavior? It's certainly an intermediate level. It's between neurons and cognition. And it's the way these things operate, firing and selecting the subset are all results of neural activity. And hopefully they enable more complex cognitive tasks. In a recent paper with Christos Papadimitriou, we show in a rigorous sense that some very basic things like memory and association can indeed be achieved with no specialized algorithm. And a question that perhaps is useful, and since it was at the beginning of neural networks, is do they give us insights about artificial neural networks even, if that's all you care about? So I guess one thing here is either with your favorite artificial neural network, you're able to simulate everything that our brains can do, or there's something more beyond what we know today in deep networks, right? So, okay. Getting back to a bit slightly more concrete things, what can we efficiently optimize and provably, right? If those pictures are not enough, well, convex functions, certainly you can minimize them. And then you can also minimize quasi-convex functions, essentially. But also star convex functions. Maybe this result not everybody knows due to Lee and Paul Valiant, where there is basically the convexity condition holds only with respect to one point in the optimum point, not one point, but an optimal point. What can we sample provably? It turns out these questions of optimization and sampling are very related, especially when you're talking about are they tractable or not. And the limits are log concave functions, which are just exponentials of concave functions, so minus convex function. And star-shaped sets. You can actually sample star-shaped sets from the uniform distribution. Now, OK, great. Click, click, click. This should be it. I'm just trying to go to the next slide. Here we go. What can we not optimize provably? So linear functions over star-shaped sets. Can you say that 5 times? Anyway, are hard to optimize, even if. So what's a star-shaped set? There's at least one point that can see everything. Convex, every pair can see. And now you can talk about the subset of a star-shaped set that can see everything, right? So there is some set, and there is some subset of points here which can see everything. This subset is always convex, because in particular you can see every pair can see each other, because every point here can see everything. If this, even if this convex core takes up almost the entire star-shaped set, 1 minus 1 over poly n, even then it's hard. And hard in the sense that you can embed clique into it. Okay, so even to approximate, it's hard, minimizing a linear function. Whereas you can sample this in time that's only proportional to a polynomial in the dimension and the fraction of the set that's convex. Okay, what can we not sample provably? Near log concave functions. Once you deviate from this log concavity by, let's say, beta here in the logarithm, then you start having to pay an e to the beta factor, e to the order beta factor in the number of times you have to evaluate the function. Okay, so that's sort of a high-level picture of the boundary. Now you can ask, what non-convex functions can we optimize provably? So one thing that I'm sure many people here know is that rather than optimize, rather than the standard convexity condition, which says that the gradient must lie below your function, you could ask for a weaker condition, which is just saying that with respect to the optimum, you're going in the right direction. You can make progress. The gradient lets you make progress towards the optimum. And so functions like that, which take you to this, still work. But this is convex in spirit, right? Wherever you are, you have a direct line of sight to the, you know how to make progress towards the optimum. So what truly non-convex functions can we optimize provably? Okay, and there is still, even here there is something. So for example, if you take a nearly convex function, so that means that there is a convex function close to it everywhere in some bounded region, then in polynomial time you can indeed optimize your mildly non-convex function, and this is based on sampling. You can sample things that are close to being convex, and therefore you can optimize. This is a result of Belloni et al. Using simulated annealing, which was in an earlier paper. In fact, this oracle that you use for optimization, where you're evaluating the function, can be noisy and adversarial. So it can lie up to that error and give you whatever answer it wants. You'll still be able to optimize. So this one is a result that I don't know how to recover with, say, gradient descent. You really have to use more structure. But nevertheless, here's an example of something that can be done. Okay, well, if that's the limit, then how do you explain everything that's going on, right? Not just the brain, but everything that you can actually simulate. So, of course, this is super exciting times. You can do all of these things amazingly well, including, you know that several papers at NIPS this year were automatically generated, right? And then, okay. I don't find it funny, but okay. Okay, so of course the nice thing is it's a universal algorithm, deep learning using stochastic gradient descent, and so okay, what's going on? Let me see. So let's take away the discretization so that we don't have to worry about which variety of discretization, step size, adaptiveness, and so on. And then you get this simplest differential equation that you're just following the gradient. And then the stochastic version, well, at every step, you're adding a little bit of infinitesimal noise. Okay? With that scaling square root 2, what happens is that the distribution of the point at time t converges to the log concave function e to the minus f. So if you use the gradient of f there in the update, you go towards this log concave function. Okay. Now, if for a more detailed study, you're trying to teach a course on this and writing down some things on the way, and comments are welcome. Okay, so let's with this in mind, let's go to the learning problem, the optimization problem in learning, right? Which is given labeled examples, x, f of x. I'm thinking of f as a real valued function. Find me a g so that and I'll stick to just the L2 squared error. The regression error is less than some target epsilon. It's an optimization problem, right? You have to find g among all possible g's. Okay, so again, this is just for you to know how simplistic is my view of this. There is what we're going to use to learn the model for G, the class of G's over which we optimize are these simple neural networks. And in fact, I will just be considering one hidden layer networks. So there is a layer of nonlinear activations followed by a linear layer, and that's the output. And this nonlinear activations can really be anything that's monotonic, sigmoids, ReLUs, etc. There will not be a constraint here in this talk on them. Okay. And of course, the algorithm that's of most interest is to just take the loss function and use gradient descent. Okay.
So do you have 2 hidden units, or is just a cartoon?
That's a cartoon. I mean, as many n units as you want. Sorry, excuse me. Yeah, there can be many, but it's just one layer. Yeah. Yeah, I should have put some dot, dot, dot. Yeah. Okay. So, what can we say about this? Something like that. Anyway, sorry. Guarantees. Of course, you want guarantees, right? Guarantees for deep learning. Provable guarantees. What if the data itself is generated by a neural network? Realizable case, right? Sort of an obvious thing to look at. Because you want small error, there better be a network that has small error. Okay, but of course the trouble, as most of you know, and it's been studied nicely in the last few years, also, is that any continuous function can be approximated with, say, sigmoid activations, but also with other activation units. So it's not going to be that easy. What if the generating neural network is small in some sense? Small with number of units, small because the weights have small norm, etc. Okay, so that's the thing. And I guess the first question is, what form could such a guarantee take? What would it even look like? I mean, how would you state it? Maybe it's a condition on the distribution and function together, right? Not just about the function, but also about the distribution on inputs. And does it actually help if it's realizable by a neural network? Does it help if you know that there is a network with zero error? Okay, so there's a lot of work on this. Avram Blum and Ron Rivest, everybody knows this result about NP hardness, even with 3 nodes. But there are, with stronger assumptions, there are other results which says you can't even learn small depth networks and so on. And Adi Shamir showed a couple of years ago that even for nice input distributions, so the lower bounds from complexity tend to be for discrete distributions and perhaps could be dismissed as saying this is not realistic. But even for nice distributions like Gaussian, gradient descent can be inefficient, is what he showed. So here's the outline of this talk, of the rest of this talk. So I'll give you an explicit, smooth, Lipschitz, as nice as you want, known input distribution lower bound for where the data is generated by a single hidden layer. Okay, a neural network with a single hidden layer. And it's going to take basically an exponential number of gradients, and much more generally, a large class of algorithms won't be able to do it. On the other hand, if these activation units are unbiased, then you can learn them with gradient descent. You can learn this with gradient descent. Unbiased meaning that the threshold is 0 or fixed. And this pull at 2 is also tight. So even if you can't do any better than this. Okay, you can't do any better than what the polynomial that we'll get. And then a couple of slides about research that I'm particularly interested in. Okay, so here's the construction without further. Here's the explicit construction. Let me know if you have an idea how to learn this. Okay, the input is n-dimensional, small n. Let's say for a second every coordinate is an independent Gaussian. So you know the distribution. I don't tell you the connectivity here or the weights. You could assume it's fully connected. I just don't tell you the weights. The next layer is nearly linear number of sigmoid units, just sigmoids. And the output is a summation. That's the architecture of the network. So you know this is the network generating the data. Okay. Now, just to be clear, when I say sigmoid, the sigmoid has this parameter S, which is you might call it the sharpness. How sharply does it transition from the 0 side to the 1 side? And I'm just calling that S. This is how the higher the S, the sharper it is. Okay. So again, but in fact, this will work you can choose your distribution. You can pick for your input, for each coordinate, any log concave distribution you want. So for example, uniform and 0, 1. Maybe you don't like Gaussian, uniform and 0, 1. Any log concave distribution. For your gate, you can pick any of these monotonic gates. Basically, it has to go up and down, or something that can realize a monotonic gate. So for example, if you had a ReLU, yeah, that's fine as it is, but others also can be put in this form. We'll see in a minute. And then the output is linear. So this is the type of architecture that is generating the purported bad distribution, hard to learn distribution. Okay, yes?
You are assuming the product distribution though? When you said
Yes, those are independent. Yeah, they're independent. Yeah.
Is the difficult case rank deficient or condition number is large?
I'll tell you exactly what the weights are in a minute, but yeah. Yeah, yeah. So I haven't told you the weights yet. So here is the lower bound. So you get to choose your favorite network architecture units. For learning, you do whatever you want. You pick your architecture. You pick your style of your what is it called, schedule, and so on. And I'm putting the theorem in quotes. I'll make it precise in a few slides. If the training algorithm is only using black box functions of the input distribution, such as gradients or Hessians, if that's all you're using, then you're going to need an exponential number of evaluations of accuracy at most 1 over S square root n. So if you think of S as a constant, say the standard sigmoid, e to the x over 1 plus e to the x, then if you're only asking for accuracy 1 over root n, and no better than that, then you're going to need an exponential number of these iterations. If you ask for very high accuracy, then there is no lower bound here. Okay, so you'd have to make your batch sizes a larger polynomial, and then the lower bound doesn't hold. I just want to be explicit. But if your batch sizes are, say, size linear in the input, then the lower bound holds. Okay, so just a little more context. So this was the construction. Now this network, for this type of one-layer network, there are algorithms, but the algorithms are polynomial in n, and the condition number of this weight matrix. I haven't told you what the weight matrix are. I'll tell you in a minute, and I already mentioned Shamir's lower bound. Now, which holds which also gives a hard example. So here is the type of algorithm we're looking at. I mentioned you're going to estimate some function of the current weights. You get to choose some function of the current weights, and using the current weights, some function of the input distribution, and use that function to update your weights. That's the type of algorithm. Okay? This function can be adaptive. You can choose it depending on the current weights and so on. You don't have to fix it in advance like gradient. Okay, so here is all I have to tell you is the weights and the thresholds, right? Otherwise, it's all fixed in the generating network. And so this is how we'll generate the hard family of functions. You start with a sigmoid, shift it a little bit, 1 over S, and then you negate it. So with 1 minus x, add those two. When you add those two, you get a little bump, right? Get a little bump. And then you're going to add many of these with the bumps placed periodically. But of course, we don't go to infinity. We only go linear number of them. So So there's a linear number of these bumps, and the function is just the sum of these. Okay, that's it. So the functions are exactly the same except for the bias, the threshold. And this looks almost periodic. It won't be periodic, of course, because you stop at n. You don't go forever, so it will have a slight decay at the end. Okay, that's the function. Now, for a ReLU, if you want to do it, you can do the same thing. You start with that, you negate it. That first you do 2 of them to give you this step function, and then you combine 2 such step functions to get a what is that, sawtooth, and then yeah, that's your function. Okay, so take any of these gates, and the plan is to all I have to do is do these biases. So here is the family. I'm going to pick a subset of size n over 2 of the inputs, and the function will simply be this sigmoid function applied to this wave function applied to the sum over that subset. So there's a subset that's been selected, and you apply this wave function to that subset. That's it. That's the output. So the only thing you don't know is which of the subset is connected to all the gates, which n over 2 is connected. And so there are roughly 2 to the n choices. Okay, and choose n over 2 choices for which subset of n over 2 are actually connected, and the same subset are going to be connected to every single activation unit. Okay, now that's rank 1, the weight matrix. You can make it full rank because the weights can in fact be perturbed by a small polynomial, and the lower bounds will still be okay. You can perturb, so it's not that it's rank deficient, but of course the condition number is high, but polynomial still. Yeah. Okay, so now you use deep learning to try to learn this. Right? And indeed, my co-author, who's one of the leading experts on deep learning, Lê Song, on this paper, he wouldn't believe it. He said, "Oh, okay, I can learn this." He has state-of-the-art architecture and methods, and so he tried. With some, he really tried. And I'm talking about small, 50 to 100 input dimension, no thousands, he tried several layers, tried one layer, alternate maxing and pooling and all this, nothing. The best error he got is 0.035. You know why 0.035 is significant? It's what you get if I output half all the time. If you just output half all the time, you get 0.035. It's the error function is half of the expected error squared. So if you're outputting half, the expected error is like 0.25, square 0.25, it's about 0.07, half of that is 0.035. I won't use the board for that, but you know what I'm saying. Okay, and you see what's happening to the error. When the sharpness times square root n is small, you're doing fine. This is with, of course, many random starts and so on. And then that's all we can get. And indeed, this is kind of holds across many different input distributions, and also for the ReLU or sigmoid. This is an experiment you can run while the talk is going on, right? Because it's freelance. Yeah. Anyway, so okay, so we tried deep learning. It didn't work. This might be more convincing than the proof I'm about to show, but I'll proceed anyway. So the framework in which we're going to prove this lower bound, so that I can state the theorem precisely, is the statistical query framework, or what are known as statistical query algorithms. And the idea is that you're solving some problem over a distribution, a search problem, or a decision problem, or an optimization problem, and all you have access to is that you can evaluate functions over the input distribution. You never get to see explicit examples. You can evaluate functions such as gradient. But this is the form of neural network training algorithms. Okay, so that's how it's working. Now, so I've already said this. The queries that you get to make are expectations of functions, and you'll get back a response to within some tolerance tau. That's the point. You get an error to within tolerance tau. Okay, so there is a true expectation, and which is say new in this case, and you get back something within tolerance tau, and you get to specify tau, and get to see this, and then you can be adaptive and all that. Okay, so these are quite general. In fact, essentially all known positive, efficient results, this is sort of a tall claim, so let me be careful. There are SQ alternatives to problems over distributions, except for one, which is learning linear equations or solving linear equations over a finite field. For that, the only algorithm I know is Gaussian elimination, and that one is not statistical query. Other than that, you want to solve a convex program? No problem. We can do it with statistical query. Okay, so that's the framework. Yeah.
Essentially, you created like a parity function with this?
Not quite, right? You saw what the function looks like, but the goal was that. We want to have a smooth parity, let's say, right? Right, that's right, that's the intuition, yeah. Good. So, but before I do that, I would like to make this notion of tolerance a bit more refined, so it's the lower bound is stronger. So we already mentioned that statistical query algorithms interact with the input distribution, but only by expectations. So there is some true expectation, and then instead of giving me a tolerance, let's say I give you an integer t, which is supposed to be the batch size. Okay, it's like the batch size. Evaluate this expectation using this batch size. Except the oracle returns an answer which is whose error with respect to true expectation is within the standard deviation of that many, of a batch of that size. So it has to return something that's within the standard deviation of that. That's the constraint. But within that, it can give just to be explicit, it can give you an adversarial answer. Okay? So that's the point. Okay, so this is a framework from introduced by Kearns with the original tolerance oracle, and this VStat we developed in the context of a different unsupervised learning problem, learning a planted clique. As I mentioned, the only known example where you have a polynomial efficient algorithm, but no statistical query algorithm is learning linear equations over finite fields. There are many SQ lower bounds for interesting problems for which we don't have efficient algorithms. Maybe some that you haven't heard about are learning planted satisfiability, satisfiability instances, and robustly learning single Gaussian in high dimension.
Are these for VStat or stat?
You actually need VStat for the last ones, yeah. Yeah, the last ones. For parity, you don't need it. Stat is as part, yeah. Yeah, for the rest, you actually need VStat, yeah. Okay, but it's also, the oracle is weaker. It can do less damage, yeah. Okay, so here is the theorem. Now I can state the theorem precisely. There exist smooth functions. You saw them explicitly, right? The family of smooth functions, smooth, Lipschitz, whatever. They're realizable in neural networks with one hidden layer of S-sharp sigmoids, just sigmoids. Only the bias we changed, such that for any log concave product distribution of inputs, you get to pick the product distribution and you know it up front. Any statistical algorithm that learns to better than a constant function, if it's strictly better than a constant function, it must use an exponential number of queries as long as its batch sizes are linear or less. Okay, so if you use n squared batch size, there's no lower bound. Okay? But if you use batch size n or smaller, n is the dimension, then you better spend an exponential number of queries. Okay. So just to give you a bit of an idea of why this should hold, remember this function family. Let me just go back to it briefly. This was the family, right? The root of the family. Just one layer. There's a particular subset that's hooked up with high weights, and the rest is hooked up with low weights, which you could think of as 0. And then all you're doing is computing this wave function or a nearly periodic function by a sum of sigmoids. That's it, and a linear number of them. So this function now, but you see, we have an exponential number of candidates now, right? One for every subset. And the point is that certainly the distributions given by two subsets, S and T, will overlap. It's not like parity where they're completely orthogonal. Okay, they will overlap. They will have, in fact, constant total variation distance, strictly, less than 1. But their correlation is actually bounded. Okay, this is the thing. For a random pair, some pairs will be close. If S and T have a lot of overlap, in fact, the distributions will be closer. but a typical one will be far, and that's enough. This notion of average correlation being small is enough to prove a lower bound. So this gives you a new notion of statistical dimension, and this dimension for this distribution is high. Just to give a few more sentences, you have this space of possible architectures, right? We've reduced them to 2 to the n architectures. You want to ask a query. You get to ask any query you want. That separates as many as possible, eliminates as many as possible. And the claim is that there are no good queries. No matter what you ask, I can make sure that what you're eliminating is extremely small fraction. So you have to ask me a lot of queries, like gradients. So that's the intuition here. And so this immediately gives you query complexity bounds. And rather than having to do this for supervised or 0-1 labels, you can do this for any continuous function and regression problems like in this case. OK, so turning to upper bounds. Back to upper bounds. OK, so that's the story there. There are a couple of things unsatisfactory about that. You see, you did not get 0 training error. Right? The error was the best error of a constant function. So you could say, what if your error could actually become 0 in the training algorithm? Maybe then it works well, and so on. So in other words, we're searching for reasonable conditions under which we can optimize these non-convex functions. So what are such candidate functions? There are many in the examples in literature now, using non-gradient descent algorithms, and using gradient descent too, with regularization, with different architectures, using for some class of polynomials, with stronger decay assumptions, and so on. Yeah? So you could view this as another in such a line, except that I will prove a matching lower bound. Okay. So here is the specific family. To make this more general, but this captures the sense of what we can prove an upper bound for. So again, the function being to be learned, the data, is being generated by a 1 hidden layer function, except now it's unbiased. You see in that sigmoid, there's no b. So it's actually unbiased. Okay? The threshold is 0. And then there is some condition on the norm of the weights at the outer layer. And the main assumption is that the function being, that given to us, the labeling function, is approximately low degree. You might not know the basis. It might not be low degree in the obvious basis, but it's low degree as a function on the sphere. Okay? So the guarantee will depend on this degree. So here is the thing. So suppose I represent f superscript less than or equal to k as f projected to degree k polynomials. Let's stick to a nice basis like the harmonic polynomials, which are a basis of functions over the sphere. Then if you project to degree k polynomials, that's that. Now let's say that there is some best degree k polynomial, of course, the projection. And our goal is to find a function, by any means you want, which achieves error that's close to the best degree k function plus epsilon. So you want to be agnostically as good as the best degree k polynomial in this sense. OK. So here is what we can do. If you use n to the k over poly epsilon units, epsilon is your target error, and by just initializing randomly, and the architecture you'll use to learn is a single hidden layer, just a single hidden layer with that many units. Use standard gradient descent, and then the number of iterations you need is also n to the order k, but only log 1 over epsilon. You'll get the guarantee you want with high probability. That in fact, the agnostic error is going to be opt plus epsilon if you use n to the k, given that the error of the best degree k approximation was opt. That's it. Okay. I want to say, how much time do I? Oh, great, thanks. There is a corollary which is more refined here, where you see the exponent doesn't have a k in it by just controlling the norms of the weights, but I'll skip that. The main idea of the proof, and maybe you might find this interesting because it's a quite general tool, is just because things are on the sphere, you get to make these nice transforms. So you see the type of update we're doing, the computing, the gradient itself, can be thought of as a transform from functions to functions on the sphere. And in particular, it's actually a func transform, you see, which is just an expectation over the sphere of whatever function you have times whatever one-dimensional function you choose. So it's a transform that is defined by a one-dimensional function of any function on the sphere. So it takes a function on the sphere to a function on the sphere based on your one-dimensional function. Okay, so in our case, that's the sigmoid, let's say, or some other nonlinear activation. And there are some very interesting special cases of this. So for example, if the function is just 1 in a hemisphere, you get this hemispherical transform. So it's just integrating in each hemisphere. Or if it's 1 on a hyperplane, it's the red-on transform. And when you use this target function h as your residual error, then the transform is the gradient. Okay, so if you're looking at residual error, the transform is the gradient. Okay, so just pictorially, this is what the transform looks like. Red is positive. Blue is positive. Red is negative. But if you look at in the spectrum, in the Fourier, in the harmonic space, that's what it looks like. This is just an example of a degree 3 polynomial. Okay, but here's the sort of really cool fact about this transform. It's called this Funkeke formula. It says that for spherical harmonics, which are the basis of these functions on the sphere, the transform of the spherical harmonic for any sigma is the harmonic itself just scaled by a constant that depends only on the function. Okay, so you get back the same thing. Now, what this means is that if you look back at what gradient descent is doing, it's just applying the func transform twice. 2 iterations of func transform is your update. And therefore, the change, the improvement in the error is proportional to the current residual error, which is exactly what you want. Then you get, you're going to make progress as long as you're far from the best possible. In fact, yes.
Are you doing gradient descent also on U or only on U?
You can do it in either way, of course. And my next slide is saying that it's enough to do just the top level. You could do just top level and you'll get the same guarantee. You can do both, but you can do just top level. So in some sense, this is like this kitchen sinks paper, right? You're starting with random weights. You're only updating the top level. Except rather than requiring, the guarantee is not with respect to functions of the similar support as the sampling density of the use, which is what here, it's with respect to the best low degree approximation. It's really agnostic in this sense. Okay, now I mentioned that there's a matching lower bound. And so the lower bound, again, is for all statistical query algorithms. And it says that there is a family of degree k polynomials. In fact, they are the spherical harmonics. Just take all the harmonics. And I don't tell you which harmonic you have to learn. There's an exponential number of them, n to the k of them. And you're seeing outputs according to that harmonic, and you want to learn it. And the claim is that for any statistical algorithm, you must take n to the k queries. And in fact, the batch size is also large. That's the trade-off here. So it matches what the upper bound from gradient descent in this sense up to the degree k approximation. Okay, the idea is similar. Random harmonics are in fact going to be highly uncorrelated. The correlation is going to be small. That's the point. So I have 2 more slides. In terms of research directions, of course, there's a sort of obvious question of what distribution function pairs can neural networks actually learn? Okay. Does having many computational layers help efficiency? I know it helps representation. I know people in this room have proved this very nicely. But does it actually help computation? Computational convergence. Can you give me one example where it probably helps? I'll be very grateful. And then again, more concretely, what real-world structure makes learning easier? So this is a variant of 1. In particular, I assumed in the lower bound that input coordinates were independent. So it was product distribution. And we use this in the proof. Does correlation in the distribution actually help you learn? Maybe it helps you. Okay, but then what kind? Okay. And then, of course, just remind you of the first 10 slides. How does the brain actually learn, and why is it so robust? Here's my philosophical slide, I guess. So feel free to tune out. An uncertainty principle. So we've been asking about generalization. So I want to ask, is there a trade-off between generalization and robustness? And here's what I mean. And actually, really, I mean over-parameterization. So here's data. This is an experiment, so you can try it out yourself. Take data from a random one hidden layer neural network. By random, I mean the weights are random. It's just one. The output is a sum. The first layer is random weights, random fully connected. There are k ReLUs, and the input distribution is Gaussian. And then you learn this. This is the data. you learn this using a model with more than k units. Also one hidden layer. If you want more than one hidden layer, doesn't matter, but you use more units. Okay, we've all done this experiment before. You know what happens. So dimension 10, k equals the number of ReLUs 10. Actually, I think the dimension was 20, but it doesn't matter. And then I tried with 20 and 40, right? The model size, 20 and 40. And as expected, the training and test errors, in fact, I'm reporting here the test errors are very small, 10 to the minus 5. And in fact, and as you increase k prime, double it, the training test error drops even more, right? This is your standard over-parameterization experiment saying as you over-parameterize, not only your training error, but your test error is also going down. But the worst error over the sphere is very high. Not only is it high, it goes up. Now, what do I mean by worst error? The error, training and test error, is over the same distribution as the input. Okay? The worst error is I just compute the worst point, the point which is the maximum difference between the true hypothesis and the learned hypothesis, which are both combinations of ReLUs in this case. Okay? And the worst error is high. And it's very easy to find these points with high worst error. Just run a simple convex program or gradient descent. Okay? So, so what it's saying is that it's easy to find an adversarial example where the error is like orders of magnitude higher. And it's not only that, it's going up. As I increase the number of the over-parameterization, this worst error is going up. Okay? So maybe if as you over-parameterize, it's easier to learn and even get lower test error on your input distribution, but it comes at the cost of being less robust. This is maybe, it's just pure conjecture. You should not take it seriously. So, is there a theory of non-convex optimization? Thank you. I'm still searching. Yes.
I'm actually curious about this V-stat versus stat. I mean, do you think that there's a real gap there? Or
Yeah, there is. Provable gap, yeah.
So for what?
So take, for example, the planted clique problem or the planted k-satisfiability problem. With stat, you get a quadratically worse lower bound than with
Quadratic in what? So
the dimension, the statistical dimension. So which means the complexity of the algorithm, the number of queries. The number of queries.
Just a polynomial gap. I mean, okay, maybe I don't care about those too much. No, because the gaps you show here are much bigger. I mean, the gaps between.
Yeah, there is a, right. There's another essential difference here, which is that stat really requires that every pair of functions in your class have low correlation. Whereas with VStat, you can get away with average low correlation. So that might be a more useful thing in the proof.
Because in a sense, I mean, the real thing we're working with is more stat than VStat, right? VStat basically says we're not allowed to query the same point multiple times.
No such thing.
No, not allowed to query with the same data multiple times.
No such thing. In both cases, VStat is a strict. All it's saying is, in one case, you give me a tolerance, and I give you back an answer within that tolerance. In the other case, you give me back a number t, and the tolerance is dictated by t. That's all.
Right, but if you think of this tolerance resulting from the batch size, as you said,
Yeah.
then I can always reduce it by reusing the same batch multiple times.
Oh, no. In neither case, you get to reuse. You only get to expectation.
Right, and VStat,
Yeah.
are you not allowed to reuse?
In both cases, yeah.
Okay.
Yeah.
All